There are other intriguing aspects of how atoms combine to form molecules. Let's take one example in particular. If we combine the most commonly occurring pure form of chlorine, that is chlorine gas, we recognize that this chlorine gas, Cl2, is extremely toxic. In fact, it was used in the First World War because it's toxic to human beings. It was a poison gas that was used routinely. And when we combine that with sodium metal, a soft, silvery substance, we form NaCl. This is table salt. This is what we ingest and use constantly, and it's clearly non-toxic, it's stable, and it's a standard fare on the table of virtually every dining room worldwide. But the remarkable thing is if we drop a piece of sodium into water, it explodes in flame. And so we take two completely different atoms, combine them together to form a molecule, and we take a toxic gas and an explosive metal and we create a stable crystalline structure, NaCl. So the next step in analyzing the creation of molecules from atoms is to recognize that this remarkable variety in chemical properties available to us represents a powerful opportunity, but we must first acquire a working knowledge of how these compounds are constructed and how do we represent that structure. So we note the close relationship here between the structure of molecules and the naming. And this is particularly important because, as we'll see, there's a close relationship between the structure of a molecule and its function in nature. So by acquiring the ability to name these molecules, we can keep track not just of what they are and what they look like, but also what they do in a chemical sense. So let's take a couple of examples, in fact a few examples. Let's take benzene. This molecule is represented in what's called a molecular formula simply by keeping track of the number of atoms contained in it, C6H6. 6 carbon atoms, 6 hydrogen atoms. But then when we move to the structural formula, we can represent exactly how those carbon atoms and those hydrogen atoms are bonded together. And we'll look at this in more detail in just a moment. And then finally there's the ball and stick model. The ball and stick model captures a lot more of the detail in the molecular structure. And in fact, there's a very close relationship between the ball and stick model and what we will establish when we study quantum mechanics. It actually tells us exactly why those molecules take that shape. Then we have acetylene. Acetylene is an extremely important molecule because it's used in an arc for welding, and it's used in an arc for welding because that C2H2 molecule has a triple bond in it that's represented in the structural formula, and it's that triple bond that forms the extremely strong bond between those two carbon atoms. So when we react this with oxygen, it releases a huge amount of energy because CO2 and water is the product. The ball and stick model is fairly simple because it's linear. Then let's look at glucose. This is the product of oxidation reduction reactions, and it's the fuel that drives organisms. But look at the symmetry. It's C6H12O6, so it's very easy to remember what that molecular formula is. It's not so easy to represent the structural formula. You have to draw that out, but contained in it is a great deal of information. When we look at the ball and stick model, all of a sudden we see something else that's coming into play. It's not just the bonds that are there, it's the bond angles that are captured in that ball and stick model. And as it turns out, in chemistry, there are two things that matter more than anything else, and that's the energy of a molecular structure and the shape of the molecular structure. So as we step to more and more sophistication in the naming of these structures, we contain more and more information, particularly regarding shape. And then if we come finally to ammonia, NH3, we can represent its structural formula very easily, but its ball and stick model demonstrates that it's got a pyramid structure to those 3 hydrogens that emanate off the central nitrogen. All right, so let's take a couple of examples and write them out. Benzene, C6H6. So we've got 6 carbons, and we're going to draw those in to form the structural formula. And attached to each one of those carbons is a hydrogen. And then the bonding structure that's intrinsic to benzene is something of slightly more complexity because there are double bonds and single bonds. And it turns out in benzene they alternate single bond, double bond, single bond, double bond, single bond, double bond. There's the structural formula that we can sketch out for benzene. And indeed it contains a huge amount of information. It turns out that benzene is planar, so the angles, all of the carbon backbone occurs in the plane of this diagram. The ball and stick model captures that, and it also shows the alternating single, double, single, double, single, double bonds. Then finally acetylene. Acetylene is composed of a carbon backbone, and the terminal hydrogens are connected onto those carbon atoms. But then there's this triple bond in the middle. And as we'll see when we progress through the analysis of how we create these structures, why we know that that's a triple bond and not a double bond, for example. And then the ball and stick model, again, captures all of that information for us.